Good evening, Mr. Rezzolla. We are so glad to have you here with your lecture about black holes and images of black holes. I have so many questions for you because we were all so fascinated with this. And the first is quite simple for you. I'm pretty sure you answered this many times. Why we took a first picture of a distant galaxy and after that, a few years later, of our own galaxy?
Okay, that's a very good question, actually. At the beginning, we wanted to take the picture within our galaxy, but then we realized this was a much more difficult problem. And that's because the black hole in our galaxy is smaller and has a variability of a few minutes only. Okay. And because we have to take an image that lasts for about 8 hours, we needed something which was more stable in terms of variability. And so we chose the other black hole candidate, M87 star, which is much bigger. It's 1,000 times bigger. Mm-hmm. This means that everything is slower, 1,000 times slower. And so the variability is of the order of a few days. And so if you want to take a photo that lasts about 1 day, you are not suffering from this problem of variability.
So for how long have you actually been exposing this black hole on your, it's not cameras, it's radio telescopes?
Right. The radio telescope have to collect the light, and it's not a single telescope. There are many telescopes, and they are all scattered across the planet. And so between the first one that sees the source and the last one, it's about 10 hours, 8 to 10 hours. That's because we start with Europe and then we end with the Hawaii. That's the last telescope to see.
And so the complete time of the exposure is how?
About 10 hours.
About 10 hours
yes.
only?
Yes.
I was expecting like half a year or
no.
something like this. And so what did those pictures show us? Do we all agree now that Einstein was right, or do we have some?
So Einstein is definitely right in the sense that all we observe is compatible with what he predicted in every detail, but the observations are still not precise enough to exclude other possibilities. So some possibilities, some alternatives we can exclude, but there are others which are still compatible. So there are other theories of gravity that also predict black holes, and these black holes are very similar to Einstein's black holes, and to the precision of this measurement we cannot distinguish them. But we can already rule out other exotic explanations, like for instance wormholes or boson stars. Those are not compatible with what we observe.
Okay, so I heard, for example, that one of the explanations of the big chunk of matter inside a center of galaxy can be a big lump of loosely held dark matter or something like this. It's now...
Right, yeah. That explanation that would also be predicting a boson star as an explanation of dark matter, that is incompatible with our observation. Because if that was the case, we would observe a much smaller shadow than the one we observe.
Okay, yes, I understand this. So the thing that I was thinking about is that how come that galaxy that is that far away is that the black hole is that much bigger? What caused the growth of the?
Well, so this is another good question. We don't really know, how black holes, supermassive black holes, are produced. But what we know is that there can be many different masses. There can be those that have tens of billions of solar masses, like M87, and there can be, much smaller ones of 1 million or even less, like in our galaxy. So I think there is a distribution, and of course, we try to get the biggest one, which was sufficiently close to us. Yes. There are even bigger than M87, but they are too far away, and so the image of the black hole will be even smaller and below our resolution. So it's a compromise between having a sufficiently large black hole and sufficiently close to us. And there are two black holes that match this requirement. One is M87, and the other one is Sagittarius A star. the one in our galaxy.
Let me get you, because you are one of the, do I understand that you are one of the designers of this Event Horizon telescope, or the way it observes?
Yes, of course, yeah. I'm part of this collaboration,
and I heard explanation of how it works, made definitely just for general public, that I can imagine the telescope like it has a lens the size of the Earth, but it's very dirty, and you clean it only on few places, so you see much darker image, but with the same resolution as if it was that big. Is it a good explanation?
Yeah, it is a reasonably good explanation. The idea is that you want to have a sufficient resolution to see something which is intrinsically very small. Okay?
Yes.
Black holes are the smallest object you can produce. And they are at very large distances, so they appear extremely small. And so you need something which is a telescope which is as big as possible, and of course you would like to have as big as the whole Earth. You can't do this, but what you can do is you can create an interferometry.
Yes.
And this means you can put together telescopes on different places, and then you can think that those two telescopes are like the only parts of a larger telescope which is actually getting light.
Yes.
And so it's like having a telescope which has mostly holes, apart from a few places where you're actually collecting the data.
Would it help, for example, if we had a big radio telescope on the moon or somewhere in?
Yeah, that's a very good suggestion. What you want is to have a telescope which is as big as possible. And of course, the planet has a limited size, but you can think of putting telescopes on the moon. That will not really help you a lot. I mean, because the moon doesn't give you a lot of flexibility. But what you can do is you can place telescopes on satellites.
Yes.
And you can place the satellites at very large distances, and there you can have very large telescope. That's what we think is going to be the future of this type of observation, taking these observations from satellites.
Okay. One thing, let me go back to these alternative theories of gravity. A few days ago, I saw a talk about Verlinde gravity, which is like different explanation of theory of relativity, which has a potential to explain other phenomena like dark energy and dark matter. Can your observations help with this, or is it something else?
Yes, so in principle, yes, because that's an important consequence of these observations, that now we can start setting very stringent constraints on different theories. So if a theory and the prediction of a theory is very different from general relativity, then it's easy to decide who is right and who is wrong. If the theory, on the other hand, is very similar, or has a prediction which is very similar to general relativity, and most of them are exactly like that, they have very similar predictions, then it will take more time and better observations to see who is right and who is wrong.
One question, I was reading about your research, even in other similar fields, and I was reading for the first time about this object called blitzar.
A blitzar, yes.
Can you tell me something about this?
Oh yes, that's an interesting story. So what happened is that about 10 years ago, people realized that there were flashes of radio waves that were not just noise. People thought in the past, they were observed even before 10 years ago, but they thought, okay, this is just a glitch in the system, and so didn't pay a lot of attention. But then people realized, actually, no, this is a signal. This is really something that is emitting a blip of light. So it's a signal in the radio wave that lasts only a few milliseconds. So it's really like a noise that you would hear in your radio, for instance, when you are listening to. And people didn't know what could produce them. They still don't know what produces them. But I had done some studies about what happens to a neutron star, which has a magnetic field, and collapses to a black hole. The neutron star is known because it has a very strong magnetic field. But when it collapses to a black hole, this magnetic field is lost and is propagating at the speed of light as a radio wave. And so here came the idea that maybe what we are observing with these phenomena, which are called fast radio bursts, or FRBs, is actually nothing else but a collapsing neutron star to a black hole that is emitting this, this light.
It just simply disappears in the visible spectrum and in the X-ray and stuff, but the thing accelerates this.
This radio wave. So
yes,
yeah, you have to think that this is the fate of an old star. There is nothing accreting, so this star effectively cannot be seen. Cannot even be seen as a pulsar because it's not rotating very fast.
Yes.
It's really a star which is about to die, and the last signal it emits would be just the shedding of this magnetic field. And it would look exactly as we observe. Now, of course, this doesn't mean that what we see as fast radio bursts is a blitzar, but it's an interesting suggestion.
One of the explanations
One of the possible explanations. I think, personally, it's the most convincing one. Yeah. We still don't know, but it's the most convincing one. Now, since then, people have done a lot more observation. When I first wrote about this idea, there were like 6 or 7 known FRBs. Now there are of the order of hundreds. And what we know is that there are those who repeat themselves and those that do not repeat. They just have this burst once and they never repeat again. And so obviously the blitzar model cannot be applied for those that repeat themselves because you cannot collapse only once. But for those that are producing the signal only once, this is the most convincing explanation.
Just remind me of this wow signal, which is something completely different, but it's much longer. But I was maybe some big magnetars colliding into black hole, maybe.
Yeah, there are
20 minutes of radio.
There are many suggestions about this.
Yes. The thing, my last question actually is, which I prepared, is that, of course, all the black holes or all the neutron stars that you are expert at are very far away. We cannot touch it or send a probe there. But a few years ago, I heard this fabulation that as we are looking for this planet X or planet 9 or something, that it actually can be a small black hole on the size of like 10 centimeters or something like this, that is lurking around sun. And I immediately said, I was like dreaming that it would be perfect laboratory for scientists like you, that you can try your theories on this object, which if it is there, it will be perfect. What can we do with it if it was there?
Well, so if it was there, you would see it in a number of ways. And one of them is gravitational lensing. So black holes distort light and they can produce...
Even the small ones?
Even small ones. It would, if it is in our solar system, the precision in our solar system it should be sufficient to see this effect. But this idea of having mini black holes, or very small black holes of the order of a few centimeters, is actually something that people are thinking seriously now because of the evidence that dark matter cannot be really explained in many other ways. And there is a window in masses for these mini black holes that were produced very early in the history of the universe, when the universe was still very hot. There are possibilities of planet-sized black holes, of the order of 10 to the 24 gram, that could have been produced then, and they are still around. And maybe, some of them could be passing through our system.
Yeah. So if there is this small black hole, or we can definitely say that there is no...
Well, no, I don't know the observations of this planet X well enough. But let's say, if there is a black hole in our solar system, we should be able to establish this rather clearly.
Yes, because I think my thinking about this, if it is like of the mass of Neptune or something like this, and we cannot see it because it's very far away. So if it is much smaller, how would it show itself as gravitational lensing? If it is that small, it will be like micro lensing.
Yeah, it would be micro lensing. So there would be an amplification. If this black hole would be superposed to another star, whose luminosity you know very well, then the passage of this black hole will produce an increase in the amplitude of the intensity. Of course, this is very small because you have very small black holes, but the precision within our solar system should be enough to measure this.
Okay, that's very nice. I saw your video about cooperation with other scientists on big projects, that it is not easy or maybe not even possible to go to do a big breakthrough without cooperation. Yep. Do you think that, for example, one contra example for me was that a few years ago there was this second object that entered solar system from interstellar space, comet kill me, I don't know, and it was discovered by amateur astronomer on his backyard, simply observing stars with an amateur telescope. And I was like, this is breakthrough. Yeah. Of course, I understand that big computational physics or stuff like this cannot be done without supercomputers and without people that are doing this. But for example, some people like to have what is the position of a new scientist who wants to do physics? What is the best way how to do it?
So I mean, it depends on how the scientist wants to do. You know, if it is an amateur, then the work that these amateurs do is very, very important.
Yeah.
You know, measuring for the first time an asteroid or a comet, this is very, very important and can be done by very small groups of people. But I would not call this a breakthrough. You know, we know that asteroids exist, we know that comets exist. So the fact that we see one is just, you know, something that we know can happen and wouldn't surprise us if it doesn't happen. But answering questions which are more fundamental, like do black holes exist? And if they do, how do you see them? How do you convince them? This is where, you know, you need manpower. That's when you can't answer this question with an amateur approach. Simply because you need to involve large equipment, all of these telescopes, for instance. You need a lot of people who calculate the possible images. So it's a matter of, you know, simply the amount of work that is needed that requires a lot of manpower.
And so if I want to be part of the big science as a teenager or something, what is the best way?
Oh, there are many different ways. If you are passionate about science, then there are many different ways, and we welcome always young people to join us. So, for instance, in our collaboration, if there is a student who wants to join us, normally this person is already within a group, and then this person is candidated for being a member with the idea that this person will work on X or Y, and then this person joins the collaboration. So we are very open to have people from all sorts of fields join this collaboration.
To be honest, many of our viewers think that seeing as many videos about science as possible will help them to be scientists. I'm pretty sure that no one in scientific community thinks so. But people who see our channel and stuff think so. So the thing is that, for example, I'm pretty sure that mathematics and stuff, like to be very basic, is the most important. But for example, if I want to go to studying like this alternative theory of gravity and have a chance of discovering something more, which path? You know, if I want to be this big. If I want to have a chance of being in a big world of physics...
Okay, so you need to study, first of all.
Study,
okay?
study.
Study. It's a bit, imagine like, you know, wanting to succeed in music, okay?
Yeah.
You can succeed in music, but you need to be talented. You need to have the skills to play an instrument well enough so that people want to listen to you. If you play an instrument badly, no matter how strongly you want to be, you know, a rock star, you will not succeed. So the same is in science. You need dedication. You need to acquire the skills. Once you have the skills, you know your mathematics, you know your physics, then you can use all of your passion and the skills, which are essential, in order to answer some important questions. So skills and passion, those are the two ingredients. And watching YouTube videos doesn't really give you any of the two. So you really have to go and study.
Okay, thank you very much for your help.
It was a pleasure.
I hope you have lots of success in your field.
Thank you. Thank you.
Later.